All right, hello everyone. So it's my great pleasure to introduce Serhii Myroshnychenko from Lake University, who is going to talk about how far apart can centroids be. Please, Serhii.
Thank you so much, Katerina, and thank you very much for the invitation to give a talk. Today, I would like to answer this question in some sense, and this is the joint work with Katerina Tatarko and Vlad Yaskin. So please, if during the talk you have any questions, feel free to ask. I want to make it accessible. And if there are any issues, whatever, please let me know. All right, so let's start by first defining what a centroid is, and then understanding apart from, like, what does it mean to be apart from each other? So let's start by introducing the main character, of course, of our story today, which is the convex body. And our convex body is going to live in, let's see here, in d-dimensional Euclidean space. And to make things more interesting, we're going to consider at least two-dimensional space. So what would be the centroid of convex body? Centroid of a convex body is like an average of the coordinates of the points inside of the body. So the definition would be 1 over the volume of the convex body times the first moment with respect to the back measure, right? So we take the average of all those coordinates. This is a vector over here. So if your convex body is something like this, right, that the point centroid will be point somewhere in the middle. And in the middle, I mean the interior, of course. And let me say, so to get it out of the way, for example, if our body is centrally symmetric, right, it means that the point x belongs to the k, then point negative x belongs to the k, meaning the centers of the origin, then of course the centroid will be at the origin. Okay, so the main question that we were interested in is the following. Let me formulate it and then explain why it's so interesting. So what is the smallest constant d that will depend on the dimension? Well, let me just say constant d depending on a dimension. Okay, now I feel like I made a bad choice of the dimension. Let's denote dimension n. That would make more sense. And then constant d will depend on the dimension. Sorry about that. Such that for any convex body k in Euclidean space and dimensional Euclidean space, the distance between the projection of the centroid, I'll explain in a second all of this, and the centroid of the projection is less or equal than d times the width of the convex body in direction u. So again, I'm gonna, oops, sorry. I'm gonna explain now, where did I go? This is not that, sorry. So let's explain the parts here. So H would be, for now, let's think about a hyperplane or hyperspace. P would stand for orthogonal projection. And if we write subscript H, it means an orthogonal projection on H. Centroid we already defined. So it's well known that if you take a convex body and project a convex body, it will remain convex. So this creature over here right now is n-1 dimensional convex body. And we're wondering about the center of this new creature. Now this D is what we're wondering about. And now this guy. this would be the width of K in the direction of U. So who is U? I'll explain in a second. So here comes the picture. Our convex body, and I'm on purpose making it very non-symmetric, gets projected on the subspace H. This is our K. Let's make it. Okay, so we project it and we obtain its shadow. So the center of the convex body, well, it looks like, I don't know, maybe it will be somewhere here. Here it is. And we project, this guy also has a center, and maybe it will be somewhere here. So this, oh my God, I'm so sorry, I should not use this button at all. Okay, sorry about that. And yes, this point over here is the center of our projection. So what we do, we project our center on the same subspace, and we obtain these 2 points. We would like to know how far apart those 2 guys can be. So the way I'm saying it right now is not very right? Because you can scale your convex body and make it as big as you want. So of course we need to avoid the scaling part and perhaps measure the distance with respect to something inside that's common for the body and its projection. So I didn't say it, but of course this is PHK. So what we're doing, we're connecting those 2 guys by a line, right? And we're considering the width of our convex body in the direction of U. So what is U right now? U would be pointing along this line, right? So again, U would be the direction parallel to the segment connecting C of PHK and PH of CK. Well, PH of CK, I should say. It feels quite natural because, for example, under the projection, the width in this direction doesn't change, right? The width of the projection, the width of the body is preserved. So yes, you can ask the same question with respect to perhaps the other internal segments of the body, but in our question and our answer, we use the width in this direction. So the goal is to, let me also say, the width is exactly this distance over here, right? So what the goal is to introduce the answer, to provide not just the numerical answer, but also the class of optimizers. And of course, I would like to talk about the proof. And it's not going to be the whole proof, but I would like to emphasize some important parts that are actually quite marvelous, in my opinion. Okay, so before we do that, please, again, if there are any questions, please let me know. But before we do the maybe general approach, why don't we start with the 2-dimensional case? This will give us a bit of intuition of what's going to happen in higher dimensions. All right, so in 2-dimensional case, our convex body maybe looks something like this. This is our K, and I'm projecting it, of course, on line. So the first thing what I'm going to do, I'm going to look at this width, right? Over here, and without loss of generality, I can scale it and make it of length 1. The center of the projection would be the center of the segment, which is the point 1/2. The center of the body, I don't know, it can be very far, very close to it, but let's say it's somewhere here. So the first step to do something to our convex body to make it look well, to make it work, the first step would be the Blaschke shaking. So what we're going to do, we're going to keep this segment and take a fiber or like one-dimensional segment inside of our body perpendicular to this line and move it down so it falls down exactly at its lower end, ends up on the axis that we're interested in. So we repeat it for all of the segments, and the shape that we're obtaining may be something like this. Okay, that doesn't look right. Maybe something like this. So we have shaped our body and kind of fell down on this line. Of course, the width hasn't changed. It's still 0, 1. Please also note the centroid has not changed because what was happening in the orthogonal complement of our chosen direction. So, the length of the head segment didn't change. So of course, the centroid will not move to the left or to the right. Okay, so this is the first step. The second step is to intuitively, again, since you already know where the center of the projection is, intuitively, you would like to kind of push the mass of the body to one side so it becomes kind of far away from the center. And to make it more formal, what we do, let's say starting at this end, we find such arrays, so well, the picture doesn't show it really well, but the array that I'm trying to find is the one that gives me the same area of this region and the same area of this region. Clearly, such array does exist because we can always look at the difference of these areas and find the point where it's 0. So performing this operation allows us to conclude that, in fact, the shape that we're dealing with that gives us bigger distance is the right triangle, right? Because again, I moved this red mass from the left to the right. I'm sorry for a very bad picture, but those two guys are the same area. And now I can do everything by hands because I know what the center of the right triangle, like where the center of the right triangle is. And it looks like it should be 2/3 over here, right? So the distance that we're wondering about, d/2, will be 2/3 minus 1/2. Let's do it together. This is, what am I doing wrong? 4 minus 3, 1, 6, yes. And which something that doesn't make a lot of sense now, but I would like to say that this is 1, 6, 6, 6, and maybe 7 over here. Right, so the idea is to bring it down and then push it to one side. So this is what you should do to obtain the maximal distance for two-dimensional case. Now, if you think about the higher dimensional case, even starting from three-dimensional, situation is not so trivial anymore because even though you can push mass to one side, you kind of has the sides, like, the things on the sides that you don't really know how to control. So right away, the same procedure will not work, but this gave us an inspiration of what we should do, and that's what I'm going to try and explain on the next step. So let's talk about the three-dimensional case. And to be honest, the same idea continues in higher dimensional cases, but I would like you to think about everything in terms of three-dimensional case for now. So let me just give you the answer right away, and I will give you the optimizer that gives us this distance. So the distance here actually looks quite nice. Well, it's a relative notion of nice, but I do think it looks kind of nice. 1 minus this wonderful thing, which turns out to be approximately this well. Now the optimizer. Well, again, intuitively, kind of, what you want to move the whole mass of the projection to one side and the whole mass of the body kind of to the other side. And this results, after rigorous proof that I would like to discuss later, into a trapezoid on the bottom, and right above it, we just build a plane that passes through the largest side of it, a plane like this. This is the rectangle. So just to make things more nicer, let me do the coordinates. So let's say this is 0, 1, 0. This point turns out to be 1 square root of 6 minus 1 over 5, 0. And this is the guy right above it. And again, of course, you can do scaling, as I'm going to discuss later. So you can always assume that this is 1 over here. So the rest, again, this is a rectangle here, rectangle, rectangle, rectangle. There's a trapezoid with these parameters. And this is, for example, one of the optimizers that we have obtained. And you can see, I hope, the idea of what I was trying to wave hand about the mass. On the bottom, we have it more to the right, and on the right, we have it more to the, sorry, on the bottom, we have more to the left. On the body, we have it more to the right. Okay, so how to get to this creature? To get to this creature, I would like you to please follow a few steps with me of the proof, of the sketch of the proof. And let's see how it goes. All right, so the step number 1, I'm going to try and give them some names to keep things smoother. So this is kind of preparations. We are going to prepare our body for some cooking to make it, you know, to put it in the right position so things work out. So what are the preparations that we are allowed to use? First of all, we are allowed to, as I mentioned just right now, we're allowed to do vertical scaling. In other words, looking even at our optimizer, we can take these upper points and bring them up as far as we want. This will not change our distance. So of course we can shrink it so that it's not too tall. What else are we allowed to do? We're actually allowed to do quite a lot if we maybe, let me introduce the coordinate system to make it nicer. So this is our x1, this is our x2, and this is our x3. So what we're allowed to do, we're also allowed to basically do hypothetical transformations in the plane x1, I'm sorry, in the plane x2, x3. So it includes the previous one, but let me state it anyway. So the scaling in x2, x3 in span of it. All right, so for example, this means that I can make this guy go as far as I want, well, you know, finitely to the left and to the right. Of course, once again, this will not change. This is the first coordinate of the centroid. Okay, we also can make our width in the direction of E1. E1 is the standard basis, I mean, to be equal to 1, right? So that's exactly what the optimizer here has. This is 1. But once again, it's up to you what width it is. Moreover, we can adjust or maybe rotate our convex body in such a way so the projection of our center on the first coordinate direction is going to be on the right from the center of our projection. So what I mean is that they will be on the same line. I'm gonna make this line to be parallel to E1, and what I want this guy to be on the right from this guy. Okay, so now the part that should be familiar to us, and this is once again let me call it Blaschke shaking again, because it is. And we're going to shake it with respect to x3 is equal to 0, right? With respect to the span of x1 and x2. So our guy is floating in the air, we're shaking and it falls down on the plane x1, x2. Oh dear, I'm so sorry. Every time. Right? Okay, and now maybe the new ingredient that we haven't seen before in R2 because we didn't have space for that, and that would be the Schwarzsteiner symmetrization. Let's see how we spell Schwarz, not like that. With respect to the span of x1 and x3. Right, so if I were to look at my future optimizer from this direction, right, looking along x1 and just kind of seeing x3 and x2, then whatever is happening here, I symmetrize with respect to this, right? And this is my kind of x3 and this is my x2. Right, so I want it to be symmetric with respect to x3. I'm sorry, with respect to x1, x3. Please note that again, none of these assumptions or adjustments change the first coordinate of the centroid. Okay, after doing this in higher dimension, this is more meaningful, but for example, in R3 as well, it's true, we obtain, let me say in particular, we already can deduce something about the projection of the convex body, and this is PHK ends up being revolution. Okay, and the last ingredient before we can proceed is, of course, why can we look for an optimizer? Why does it exist at all? To answer this question, we're going to use once again, Blaschke, but different Blaschke, same Blaschke, but different result, Blaschke selection theorem. Let me explain why it's applicable here. So since we're allowed to scale it, as we just discussed, we can agree that inside of our convex body, we can squeeze, first of all, a segment parallel to x2, let's say of length 2. Then this is x2. Then along of x1, we agreed that the width is equal to 1. So I can say that this segment is equal to 1. This is 1, this is 1. And then since again, the height is up to us, it cannot be 0. Let's squeeze a segment of length 1 along the direction of x3. So this is 1 as well, right? So altogether, what we end up building inside of our body is a simplex. This simplex lives inside of K. On the other hand, again, according to our agreement, this guy that our result of all these preparations of K will be contained inside of the box, right? Inside of the box, let's say square over here and the height 1 over here, right? So this guy lives inside of that box. By the way, the volume of the box and the volume of this simplex are not going to be 0, right? So in other words, our optimizer will not lose the dimension, right? And then I can say that the theorem applies. this concludes the first step of our proof. All right, step number 2 is something that we are gonna maybe not use so much, but something it is nice to observe right away before we construct any further things. What did I denote at step 1? Okay, step 2. I would like to note, and this is not necessarily three-dimensional case, I would like to note that this sequence of these distances, of this maximal distances, in fact, is non-decreasing. So remember, the dn, we denote this distance for dimension n. So it turns out that these distances are not going down. So how can we see that? To see that, it's simply, the idea is to look at the cylinder. But let me just write down so we see it all together. So let's say we found our K, our optimizer in n-dimensional space. What we're going to do, we're going to look at the body M, let's say, which is the cylinder with the base K. This guy lives in, of course, n+1. Then, based on this construction, let's make two simple observations. The centroid of the projection of K on a subspace H, by the way, who is H? H is going to be the, and let me not write anything, it's just the subspace inside of hyperplane inside of En. This ends up being equal to the first, once again, this is, I'm talking about the first coordinate, right? The projection on x1. This ends up being equal to the projection on the span of H and squeezing an extra dimension x0 parallel to the 0, 1. Of what? Of course, of M. And similarly, the projection of the centroid of K actually end up being equal to same thing over here. Right, so already if you have an optimizer in previous dimension, in higher dimension, you can look at the cylinder, and this, for the cylinder, the distance will be the same, but there may be even higher, bigger distances. So we don't know, and that's why we conclude this part. Okay. Again, this is nothing to do with the previous step very much. It's just observation about the fact that the distances will be non-decreasing. We'll use it a bit later. Step number 3, maybe in some sense my favorite step, and this is where we're dealing with projections. So let's scroll back up, sorry, to where we were. After all of this constructions, after all of these preparations in the previous part, we end up with the body of revolution in the projection. And let's again start thinking about it in terms of three-dimensional creature, which means that our projection is two-dimensional. So let's look at our plane x1, x2, right? And the guy that we have probably looks something like this. Why make it look symmetrical? Okay, so this is our projection. Okay, so for this two-dimensional region, what I can do for any fixed direction in that plane, I can always find a line that splits the area of my projection in two equal pieces. Right, for a given direction, I find the line, let's say, perpendicular to it, so such that this guy, the area of this piece over here is equal to the area of this piece. If I change the direction, I can find another line. Clearly, they're changing continuously, so there are many lines that split our projection in two equal areas, into regions of two equal areas. Okay, so now I'm going to add an extra dimension in here. And based on the choice of this plane, on this lines over here, I'm going to build a plane by, adding the dimension like this. So maybe I shouldn't draw x2 this way, but it doesn't matter. Like this. So let me maybe make some notation. If this is psi, and then let me denote this line that splits L psi, splits the projection into two convex bodies. Let me give them some names now. K1 and K2. They're two-dimensional guys. Such that, yes, again, their areas are the same. Again, there are many such lines for as many directions as many lines. So what I do now, I add an extra dimension. So I'm going to look at maybe, let's call it, how did I call it? I didn't call it anyhow. Let's call it G. G would be the span, maybe G of psi, is the span of the guy in the projection plus the third coordinate. So what do G psi do? Those are, of course, the two-dimensional place in R3 in three-dimensional world, E3. And what I'm claiming that we can find G psi, maybe some particular direction, such that G psi naught splits now my convex body, K, into two clearly convex bodies. I don't want to give them any names, but these are the bodies for which the projections are K1 and K2 of equal volume. Such a plane exists because, again, you can consider the difference between the volumes on the right and on the left. This difference ends up being an odd function on the circle in the plane, which means that such function has a zero. So direction gives me zero will give me exactly the plane that does the job. So what have we obtained after this step? We obtain a plane that is parallel to x3 such that it splits the projection into two equal pieces, and it splits the whole body into two equal pieces. When by equal, I mean the volume. Okay, then let's play with those. And now I feel like I do need to give them names. And I already used K1 and K2, so let's use K1 and K2 tilde. Sometimes I change my mind. Okay, so what do I want to do? I want to look at this maximal distance. This is my D3, but let's avoid the index for now. This is going to be the, as by definition, we agreed, this is going to be this minus this. By the way, K is the optimizer right now, right? I'm trying to understand what K is, but I know that K is the optimizer. Based on our choice of the plane of the splitting plane, I can write down the center of the projection and the same thing with the center of the whole body as the, well, we know it for any, but here in particular as the average of the two centers, right? And the average, I mean exactly 1/2. So what I mean is the following. pH of CK1 tilde plus pH CK2 tilde over 2. This is our first term here. And then the same thing for, for the second term. The second term will have C's. So pH, maybe I can start using the notation I just introduced. The same for the projection. Okay, then I can rearrange it without any deep knowledge. I would like to write it down. So I would like to take the first term here and first term here. Still divided by 2. And the same thing here. Divided by 2. Okay, well, nothing deep is happening on this line. But now, in fact, I can bound it, right? Because K1 and K2 tildes are convex bodies in R3, and I know that the distances for them, which are exactly the numerators of our new 2 fractions, bounded by this maximal distance times the width of our body K1, let's say, even tilde over 2, plus the same thing for K2 over 2. Again, this is because the K is the optimizer. So whatever we get for K1 cannot be greater than the thing that we got for K. Okay, but I don't know exactly what happens to the width, but I do know that each of the width cannot be greater than the original width. So this ends up being this. Okay, so the conclusion that we're making is, in fact, all these inequalities in here ends up being, all these inequalities in here end up being equalities. Because we start with D and end up with D again. This is quite meaningful because, in particular, we conclude that the width of these splitted pieces is going to be 1. And moreover, both K1 and K2, and I'm talking about, the 3-dimensional parts, are optimizers as well. Okay, so let's come back to this picture that I drew before, but I don't want to look there. It's a bad picture. Let's make a new one. So we had this, our x1. This is our width from 0 to 1. And I have something, I don't know, something like this maybe in the projection. This is the body of revolution. So what we do, we cut the projection in such a way, we need to cut it in such a way so that the area is decreased, by 50%, and the width doesn't change. But even on this picture, you see, if I do it like this, for example, the width changes, right? Because the width of the guy over here will be strictly less than 1. So again, I'm not trying to give all the details here, but you probably can see that this means that our projection shouldn't be looking like this. It should look at least like this, right? So it does have some pieces of non-trivial lengths on each of the sides, but moreover, it's not enough, right? Because I can do splitting like this, and sure, everything looks okay, but then I can repeat, right? And I can repeat my step over here now for this upper part and do it again. Again, and again, and again. Every time I should be getting the area should decrease, right? Strictly decrease. But eventually you see that I will be in trouble again, because I will end up having the width, I will end up having a region for which the width is strictly less than 1, which is not allowed according to our earlier consideration. So what's the remedy of this situation? The remedy is that this is possible only when your body revolution has flat sides. In other words, our 2-dimensional projection is a trapezoid. Because again, if this is trapezoid, this is the only way it's going to work. So let me draw the conclusion. So repeat the above as many times as you want, and we conclude that it's possible to work, these things work out if and only if K1, for example, let me just say the whole projection, PHK is a trapezoid. And right now I live in a three-dimensional world, right? So in higher dimensions would be body of revolution with flat sides. So this way we have handled the projection. We have obtained that this projection is actually trapezoid. Okay, and now probably our two last steps. One will be bigger than the other, but step number 4, and the name for that I came up with is raising a roof. Right, so now we know what happens to the projection, right? If we look from this side, we know what's happening here, but we just need to figure out what to do with this pile above it. And this is where we're going to handle it in more analytical approach. Okay, so what we're going to do, we're going to agree, this is my K. Let's just agree that this top part over here will be a graph of the function g of x1 and x2, and this is my boundary above the projection. So for example, K in this case will be a set of points such that the first two fall in the projection, right? And x3 will be everything between the roof and the floor. And now I'm going to introduce the guy that will actually be our optimizer, although it's not, you can really see it right away. This is the same set, but here, instead of g, I'm just going to take the simplest possible function. Maybe not the simplest, not a constant, but just x1. Right? So in other words, this is equal when this is equal to x1. Okay, so let me do some light computations based on this assumption. By the way, since we already agreed that those are lines, let me just maybe give them some names. So let's say this is y is equal to ax plus b, right? Just a line in two-dimensional space. Okay, so based on our agreement, let's say that our k, the volume of our k, of course, is the integral over the projection of our roof, which after the change of the coordinates can be written like this. And yes, I will explain what capital G in a second is. I feel bad using capital G. Let's use capital T, because we already used G for a plane earlier. Where, of course, capital T is going to be integral from 0 to 1, the roof, and something like this. Just change the variables. Okay, so this function as a function of x1 is concave. Why is it concave? Because actually G is concave. Exactly as you would expect the roof of a convex body looks like, to look like. And simultaneously, since we're talking about the volume, why don't we find the volume of L, which will be easier. Dx. So remember, we're allowed to scale our candidates vertically as much as we want. So why don't we scale L and K vertically, and by vertically I mean along the last coordinate here, along the x3, such that the volume of K is equal to the volume of L. Under this assumption, repeat me, looking at all of these calculations, we can see that the integral from 0 to 1, the difference of these volumes will be 0. What's the difference here? The difference is exactly what you would expect. Yes, this is just equality of volumes. Okay, so this is 0. And now we just need to handle the first moment. So the picture will be like this. Our t, this is our x1, our t is going to be a concave function. And x1 is just a line. So there exists a unique point, let's call it alpha such that t of alpha is equal to alpha. Right, this is where they're intersecting. What did I drew? I drew t of x1, and this is just, say, y is equal to x1. Yes, such that t, sorry, I already wrote that, alpha between 0 and 1. But then all we have to do is simply look at the difference of the moments. Keep using old notation. Right, this is what we have in the numerator of our centroids. Right, this is the difference of them. Well, this, based on our earlier assumption, in fact, can be written in a harder way, but the harder way is going to help us. And I mean this. Here, of course, x1, x1. This is true, right? Because alpha times this is going to be 0. And now we feel very good, because if x1 is between 0 and alpha, I have, well, this is always positive, and this is clearly positive as well. But this will be negative. And if we fall after alpha, somewhere after alpha, but before 1, then the first is still plus, but then it's minus plus. So the conclusion is that this is less or equal than 0. Which of course implies the relation between the first moments and we're done. Because turns out, as you can see, with equal volumes, the first moment of L is greater or equal than the first moment of K. And equality holds only when T is equal to x1. Okay, so I know that I'm almost out of time, just 2 more minutes, I will be done. I just want to say that it's hard to find the exact values of distances in any dimension, because it requires the solution of polynomial equation of higher degree. But for example, in R3, it's easy to do. But what we have observed based on our earlier observation that dn plus 1 is greater or equal than dn, we observed that, of course, all of those guys will be bounded from above by the supremum of the dn. And this ends up being the limit. And this is approximately, you see, it doesn't grow too fast. It ends up being something like this. N goes to infinity. This is how we end up with the bound for any dimension. And just to conclude, I just want to say, I guess I want to say how all optimizers are going to look like. So all optimizers in all dimensions will look pretty much the same way as they look here. You start with any convex body L0 in n minus 2-dimensional space. Then you scale it a little bit and move it parallel. Keep it parallel to L0 and move it along x1. Maybe I should draw x1 somewhere here. So it's a scaled version. L1 will be the scaled version of L0 plus some shift. I don't want to say anything. It just, shift along the x1. This will be your L1. And then you build L2 equal to L1, but rest right above it. Right, so it's kind of, again, the same pictures that we had in R3, but you start with, again, n minus 2-dimensional convex body. And yes, you probably are wondering what would be the answer if we project on subspaces of higher codimension. It's even harder to find the exact answers, although it's possible to write down the expression that you need to optimize, and we did it in our work as well. So check it out. Thank you very much for your time. Let me know if any questions.
Thank you, Sergei, for a great talk. Are there any questions?
I have a question. How do you find the supreme? Is it because you know the optimizers?
I don't know if I can answer it in a trivial way. It's a work. We need to deal with this integral over integral situation, and there's no short answer to this. Unless, I don't know, Katya can correct me here.
No, but yes, Beatrice, it's because you also know the form, how optimizer looks like.
Sure, that does help.
And as far as the optimizers go, out of your proof, it looks like they're unique up to scaling and all the transformations you're allowed to do, right?
Right, and up to centralization, scaling, but well, unique up to here. Let's see, here you start with any, n minus 2-dimensional.
Okay.
Any other questions? All right, if this is not the case, then let's thank
Just one
Sergei.
more question. In your work, you can deal with any codimension or a fixed?
Well,
Fixed codimension, if you're.
Yes, it's like D, K, M.
No, but you're asking about K being fixed, right? That's what you're saying. Yeah.
You can describe it though for any K, right?
Fixed K.
Yes, for fixed K, for fixed, yes.
We don't know the asymptotics if you mean if K is.
Okay, yeah, that's what I mean. Does it have to be something small compared to the dimensions, or it can be fixed? Okay. Thank you.
All right. Okay, so let's thank Sergei again, and thanks everyone for coming.